Just a second, please. Yeah, okay, I'll press the share now. Okay, can you see? Can you see the presentation?
I can see it, yes.
Yeah, okay. Yeah. All right. So, sorry, let me get back to the first one. So the question that is at the title of the talk is everything physical? And I will, this will be one of the main basic ideas that I will explore today. The Back to Basics one will start with this idea that everything is physical. This is the first commitment that not everybody accepts, as we will see today, and we'll see that it's not trivial, and we'll explore some of its implications. So by saying that everything is physical, what I mean is this: the actual microstate and actual microhistory, as described by fundamental physics, are everything that there is. Let me say a few words about what I mean by the term actual, and then explore some of the other terms here. So, by actual, if we look at the state space, in the state space, there are infinitely many microstates, and at each moment, only one of them is real. It sits on the actual history of the world, on the actual trajectory. All other trajectories are not real, they are counterfactual. And all the microstates that are not the real one at T1 are counterfactual at T1. When we observe a system, we see its actual microstates during the time of observation, not the counterfactual ones. Although the macrostate that you ascribe to the system contains infinitely many counterfactual microstates, all that we see when we look at the system is, of course, its actual microstate at the time of observation, because this is everything that there is. This basic observation has implications that we will explore today. So this is what I mean by the actual microstate and microhistory. My commitment is that these microstate and macrohistory, as described by fundamental physics, are everything that there is. Not everybody accepts the commitment to fundamental physics. Some people add a hypothesis about physics that don't come from the fundamental theory. For example, a past hypothesis or postulates about statistics. Some people in other fields endorse ideas like God and the soul that don't come from fundamental physics. I am committed to fundamental physics and to the idea that everything is to be fully explained from these theories. We call this commitment to fundamental physics flat physicalism, and today I'm going to explore some of its implications. I now proceed to basic commitment number 2. The basic idea number 2 is that the second law of thermodynamics is not a theorem of physics. This is, of course, not a trivial statement, but it is a basic one. By this statement, what I mean is this: the second law behavior, as we experience it, is true along the actual micro trajectory, but it is not provable that most of the micro trajectories are thermodynamics. When I say that it's not provable, what I mean is that it's not provable from fundamental physics, which is the basic commitment from which I start. And this is the case even if we assume a suitable dynamics. Why is this the case? Why isn't the second law a theorem of physics? This non-trivial idea involves many arguments, and I will go very quickly and very roughly on just the headlines of these ideas and focus only on one of them. So why is the second law not a theorem? The positive route to the second law is about proving the second law from fundamental physics. Here, there are two of the problems are the following. Fundamental physics doesn't break the temporal symmetry, and therefore it cannot solve the minimum problem. A famous example concerns Lanford's theorem, as was analyzed, for example, by Uffing and Valente. A second problem here is that fundamental physics doesn't entail a measure over initial condition. Here, the typicality arguments that are very popular in contemporary foundations of physics choose a measure over the microstates that will make the actual observations expressed in thermodynamics, that will make them also typical. This is useful for predictions. It's a very good idea for physics as far as physics is concerned with making predictions. But it does not explain nor prove the second law from fundamental physics. And therefore, this is a kind of argument that begs the question. So the positive route to the second law doesn't work. There is a negative route to explore the second law, and this is by examining a counterexample, the famous one being Maxwell's demon. The second law may be true in our world, so maybe there are no Maxwellian demons in our world, but there is no proof from fundamental physics that Maxwellian demons are impossible. Specifically, there is no proof from fundamental physics that Landauer's thesis, that is often invoked to exercise Maxwell's demon, is true. In fact, fundamental physics entail that it is false. And this is the focus of what I'm going to discuss next. So, sorry, why doesn't it move on? Okay, so the third basic idea that I'm going to discuss is that Landauer's thesis is not a theorem of physics. Recall what the theorem is. Every physical implementation of a logically irreversible computation, for example, erasure, is invariably accompanied by a minimum k log 2 of dissipation of energy per lost bit of information. This theorem is often used, as I said, to exorcise Maxwell's demon and thereby explore the negative route or remove or solve the negative route of exploring the second law of thermodynamics. Here, in examining the proofs for Landauer's thesis, I want to make a point that is not only basic, but is also, I think, trivial. And it's the following one. When disproving a counterexample to the second law, for example, Maxwell's demon, you cannot assume the second law. Or when proving a counterpart of the second law, for example, Landauer's thesis, you cannot assume the second law. This idea about not begging the question is not, it turns out to be not a trivial one in contemporary discussions of the point, but I want to emphasize it. And the reason is the commitment to fundamental physics. I try not to bring into the picture anything that cannot be proven from the fundamentals. Let me now turn, in order to explore Landauer's thesis, in light of this trivial point, and in light of the commitment to fundamental physics only, let me explore the standard example brought in discussions of Landauer's thesis. And it is this. The logical operation, the logically irreversible operation that is that in most cases is brought as an example, is the operation of an erasure. Here, what we have, let me look at some details of this very well-known example. So erasure is carried out by starting from some macrostates that stand for 1 or 0 before the erasure, and then mapping them to another state, a standard state, for example, 0. And because of Liouville's theorem, this requires expansion of the macrostate along the non-information bearing degree of freedom. And therefore, entropy increases. It was 1 rectangle before, and the size of 2 rectangles in this example after, satisfying Liouville's theorem. The reason why there is an erasure, and by erasure I mean that the initial state is not, cannot be retrodicted from the final state. The reason that this takes place is that along the non-information bearing degree of freedom, the macro variables y and z are not distinguishable. So if we know that the final macrostate is 0 y plus z, we cannot infer the initial macrostate. What is the dynamics in this case? Here is a standard way of thinking about it. The idea is that if before the microstate was somewhere in the macrostate 1x, then after it will be, for example, in the gray area that is illustrated here. And similarly, in the case that we started by 0. Here too, erasure takes place because the initial macrostate cannot be retrodicted from the final macrostate. And the reason is that the macro variables y and z are not distinguishable. Entropy increases as dictated by Liouville's theorem, or so it appears in this, and in this case. The dynamics here is blending. It blends the regions 0y and 0z to make them one indistinguishable, or so it appears, region. So this is the standard example with the standard dynamics that many people have in mind. And here is a slight variation of this example. The different example differs from the previous one only by making the macro variables y and z along the non-information bearing degree of freedom distinguishable. This requires a better measuring device or a different observer. Here, an erasure takes place because the initial macrostate cannot be retrodicted from the final one because of the blending dynamics. Each of the initial macrostate is mapped to both of the final macrostates, 0y and 0z. Since there is no retrodiction, there is loss of information. This is what we mean by loss of information, because of course at the micro level, in classical mechanics, for example, there is no loss of information. Entropy in this case, however, is conserved because the measure of the final macrostates, each of them, is the same as the measure of the initial macrostates. This, of course, is not a standard case that we have in mind. People have in mind cases of dissipation, but when we explore whether or not Landauer's thesis is a theorem, what we need to look at is a suitable counterexample that is compatible with fundamental physics, not assuming the second law. And fundamental physics is satisfied by this example. Therefore, this example is a counterexample for Landauer's thesis. And if this, since this thesis turns out to be not universal, it turns out that a Maxwellian demon is a possibility according to fundamental physics. Again, not assuming the second law of thermodynamics. What I want to emphasize here, that the only difference between this different example and the previous one, which was the standard example, is in the distinguishability of the macro variables y and z along the non-information bearing degree of freedom. Therefore, we can see that Landauer's thesis depends on the partition of the state space into macrostates according to macro variables. All the partitions of the state space into macro variables are on a par as far as fundamental physics is concerned. There is no preference for any of the partitions that comes from fundamental physics. If there are preferences for certain partitions, if certain partitions are more interesting or more corresponding to our experience or something like that, this is an information that we need to bring from our experience and not to take it from the fundamental theory. Again, the conclusion is that Landauer's thesis is false. There is no way to save this, this thesis, but to see in what sense it cannot be saved, it is useful to explore another aspect of this thesis, an aspect that is not usually discussed in foundations of physics, but is discussed in foundations of cognitive science, because in cognitive science, people are interested in the notion of computation as part of the computational theory of mind. The idea is that the mental is computational, and therefore the question of how to implement a computation in the physical brain is of great interest to them. So I proceed to basic idea number 4, and the point that I want to make is the following. Here I repeat Landauer's thesis. The thesis is about physical implementations of logically irreversible computations. And the one question that needs to be asked here is, what is a physical implementation of a computation? In the philosophical foundations of cognitive science and computational neuroscience, what people found is that to implement a computation, you need actually 2 elements in a system. You need a suitable dynamics and you need a value assignment. Let us see what this means by way of an example. Consider a system, a gate that has 2 input ports, A and B, and 2 output ports, C and D. Each of the ports can be in one of 3 macrostates, or to have one of 3 macro variables. Those can be ranges of voltage, ranges of position, etc. We choose here a particular dynamics in order to make our point, but you'll see that it's not difficult to come with to propose other cases. So the dynamics that we have here is this: if the input port A happens to have the value X, then C at the output will have the value Y, and so on. In other cases of A, C will be X. If B is X, then D is Y. In all other cases, D is X. This is the very simple dynamics of this gate. Now we will explore 2 value assignments for this system. In case number 1, if the macro variable is X, then we will say that the state of the system, or the value that is implemented, is 0. And if the state, the macro variable, is Y or Z, we will say that the implemented value is 1. And we have the second value assignment. Now, both value assignments are simply more coarse-grained macrostates. This is all that there is to it. And we need to pay attention to this when we discuss the foundations of physics. Now let's see what happens in this system with these 2 value assignments. In this table, and I'm not going to go into its details, you'll see that it's a very simple one. We have a description of the dynamics. I go here over all the lines, all the 9 possibility of inputs A and B. And then we apply the value assignments 1 and then value assignment 2. It turns out that if we employ value assignment 1, the computation is logically reversible, whereas if we employ value assignment 2, the computation is logically irreversible. Now, these are the two computations differ only in the value assignment. This is the same microphysical process. And the two partitions, two macrostates, are on a par as far as fundamental physics is concerned. The two can be thought of. How to implement them is a very interesting question that we'll explore in a moment. What does it mean physically to have a value assignment? How to fix the partition to macrostates? But at this point, what we need to pay attention to is to the fact that all the partitions into microstates in the state space of the system are possible, are on a par in that sense. So we have here a system that carries out two computations, one of which is logically reversible, the other of which is logically irreversible. And the implications are the following. For Landauer's thesis, the implication is that the process is both dissipative and non-dissipative, or so it seems. So if this is the case, then the thesis entails a contradiction and is therefore false. With respect to the computational theory of mind, according to which the mental is computational, the consequence is that there are two entire minds in one brain. According to computational, to the philosophy of cognitive science, or according to cognitive science itself, in the computational approach endorsed there, the mental is computational. Mental states and processes are computational states and processes. So if we have two possible computations, two, in fact, actual computations that take place during the same microphysical evolution, then the thesis turns out to be false empirically. Here, it's not a matter of contradiction, but a matter of empirical inadequacy. The idea is that empirically, we have one entire mind in which we can carry out parallel computations and so on, but this is in one entire mind. And if we have two computations, there are two entire minds. And this is this doesn't fit the empirical assumption. So it turns out that the multiple computations theorem that was illustrated in the previous example has these two very strong implications. And the question that arises is how to solve these problems. How to think about dissipation in physics, and how to think of computations in the mind. When thinking about ways to solve these problems or to understand what's going on, we need to keep in mind the commitments, the metaphysical commitments mentioned before. Namely, we're committed to whatever is implied by fundamental physics and nothing else. So what can be the solutions? Landauer's thesis is false. This we already saw in the first argument that I illustrated with an example. But what we do understand now, what actually Landauer's did teach us, the way that we think, the need to think about Landauer's thesis teaches us that dissipation is relative to the details of the system and its dynamics, and more importantly, to the value assignment, that is, to the partition of the state space to macrostate, which is to the observer or user. Different observers, different users will look at the same system using different partitions. Different observers will be sensitive to different macro variables and to different levels of coarse graining. And these differences of the different observers will impose on the system different partitions to macrostates, and therefore, from their perspectives, different dissipations. Dissipation turns out to be a tricky idea if we understand this and we are committed to fundamental physics only. Of course, even if we take, pay attention to this lesson that we learned from Landauer's thesis, we need to remember that the dissipation has nothing to do with whether or not the logical operation that is implemented by this process is logically reversible or not. It depends on the details and specifically on the value assignment, that is on the partition to macrostates. Now, if we say that the user that looks at the system and imposes from the user's perspective a partition to macrostate, the question arises, what is the user or observer in physics? What does fundamental physics have to say about the user? If the user or observer is not described by physics, then physics is not physical in that sense. Physics will be dualistic, will put into physics something that does not come from fundamental physics. And therefore, the commitment to fundamental physics will be violated. So what can we do? How can we understand the observer in terms that are in line with the commitment to fundamental physics only? This takes us to the computational theory of mind and actually to philosophy of mind more generally. So what happens with the computational theory of mind given the multiple computations theorem? Empirically, as I said, the assumption is that we have only one entire mind in a brain. And the question is, what prefers one value assignment or partition to macrostates? Here, the problem is that there are no observers or users. Perhaps it's useful to consider the laptop or smartphone on which you're looking right now. You understand this laptop or this smartphone as a computer that carries out a particular computation. But this is imposed by you as an observer that looks at that physical system in a certain way and not in another way. An alien that has different senses and different capabilities may not see that this system carries out a computation. So the computation is relative to the user. This is how we could solve the question of which computation is carried out in your laptop and what is the dissipation that takes place during that computation. However, when the computation is said to take place in your brain, there is no further observer. You are the observer. And if we say that what fixes the computation in your brain is an observer, this is a homunculus fallacy or a regress that is brought about by considering observation by the environment. So this line of thinking is not available in order to decide or to fix what computation happens in your brain. The only way, if we accept that everything is physical, that everything comes from fundamental physics, the only way to solve this problem and without the homunculus fallacy is to endorse reductive type identity physicalism, which is the idea that the mental processes and mental states are understood as physical processes and physical states that have nothing to do with computation. We don't need even to mention the term computation. Computation can be used as a convenient way of describing something, but it's not fundamental. For those of you who are in philosophy of mind, there is no multiple realization involved here. This is a reductive idea in which everything is physical. This is the result of flat physicalism. According to flat physicalism, we start from fundamental physics, we go through statistical mechanics, and we end up with results concerning what is the mind, what is the mental, what can physics tell us about this. Let me sum up by the basic idea and the outline of the argument that I described today. So the assumptions are that everything is physical and that we're not going to assume the second law when proving or disproving it, and nor are we going to introduce into our thinking anything that does not come from fundamental physics. Those are the basic commitments. If we're committed to those ideas, then several things follow. First, Landauer's thesis has counterexamples. Therefore, it is false. It is not universal. It may hold in specific cases, but it's not a theorem. Therefore, it does not exorcise Maxwell's demon. Second, dissipation, if it happens, and to the extent that it happens, depends on partition to macrostates, which are relative to the user or observer of the system. Third, the user or observer of the system who fixes the partition to macrostates is a physical system. If it is a physical system that has mental states, then those mental states that fix the macrostates of the computer that it uses are physical macro variables. The computational theory of mind is false. If the observer is a measuring device, then it is just another system of the world to which macrostates can be ascribed in any possible way. The only system that can prefer one partition to macrostates over another is a user with mental states, which are physical state. There is nothing beyond the physical if we are committed to flat physicalism. Thank you very much.
Thank you so much. All right, so we have some time for questions. Before we get started with questions, I just want to make a couple of quick announcements. A lot of people joined after we'd done our informal introduction, so I just want to thank everybody for joining us. And now we'll take questions. So if you could use the hand raising feature, for those of you who are unfamiliar with how to use the Zoom tools, you click on the participants button on the ribbon at the bottom of the Zoom window, and then you should see a number of icons. One of the icons is a hand raising icon. I will call on people whose hands are raised. I'll just ask that after I call on you, please remember to lower your hand. If you'd like to ask an additional question, please lower your hand first and then raise it again, so that will put you at the end of the line, at the end of the queue, so you'll have a chance to ask again. We finished a couple of minutes early, so we'll have some additional time for questions, and then we'll have time for a break. I'll make sure to schedule a 5 to 8 minute break before the beginning of our next talk at 1 o'clock. All right, so with that, let me start getting to people's questions. Alyssa, please unmute your microphone, and please lower your hand too.
Oh, okay. So thanks, Orly. It's great to see you. Now, I just wanted to ask about, you were saying that for the computational theory of mind argument, that empirically there's only one mind. Can you just say more about where that's supposed to come from? I mean, it's not like, is it supposed to be like, it just seems like there's one mind?
Yes, well, this empirical assumption is the starting point in these in the cognitive scientific theories here. Now, unless you can decide for metaphysical or other reasons not to accept this empirical assumption. It is not trivial what assumptions we can make about the mental and how we can test them or verify them. So to the extent that there is one entire mind, then we need to decide which computation takes place. Some people don't accept this empirical starting point. And they say that why not assume that we have these infinitely many, in fact, minds, because we can partition the state space in infinitely many ways and assign values in infinitely many ways. And then we have to have a suitable theory of mind in cognitive science, in psychology, in brain science. This has all these implications. So, the conclusions that I presented with respect to the computational theory of mind also depend on this assumption. However, even if you accept that there is more than one entire mind in one brain, still you don't have to accept the computational theory. And here the argument is a bit different, and I won't go into all its details here. Here the idea is, just as a headline, is that the computational theory of mind is a form of functionalism. And functionalism, one of its main ideas, central idea, is multiple realization. However, multiple realization is incompatible with physicalism. It's not that physicalism is just one option for the metaphysics of multiple realization. What I'm saying is that the fundamental physicalism is incompatible with multiple realization. Multiple realization is a form of dualism, either substance dualism or property dualism. But this is a kind of, this is an argument that I did not go through today, and I'm happy to describe it to you in another time. We also wrote about this. So that's the main point.
Okay, I have Isaac Wilhelm next.
Okay, thanks very much. I was just wondering what you take the second law of thermodynamics to be such that it isn't provable. I was also kind of wondering what, if you have an account of what it is for something to be fundamental such that it would be like infelicitous to add in typicality assumptions into my stock of fundamental stuff and call that fundamental.
Well, the basic commitment that I start from in this account is that fundamental physics, for example, mechanics, quantum mechanics, take the best available physical theories that we have at the moment. Those are the full account of what there is. And here, because of the mathematical nature of these theories, we also have to add initial conditions. So in classical mechanics, just as an example that is not, of course, the best that we have, everything that there is the equations of motion into which we plug in all the parameters, etc., and the initial conditions. And that's all that there is. Of course, we can have counterfactual initial conditions, and those may give rise to a counterfactual trajectory. This trajectory is a very useful tool of thought, but it is not real. It is a useful tool of thought. The counterfactual trajectory and the counterfactual microstates at each moment are very useful tools of thought. They are what gives rise to macrostates. And macrostates are what gives rise to entropy and to the way that we understand entropy and probability. So counterfactuals are essential tools of thought for predictions. In that sense, they are a very good idea to accept in physics. However, counterfactual trajectories can exhibit very different behaviors from the one that we actually experience. And the question is whether we can explain why the things that we experience are those that are you know, that the ones that take place along the actual micro trajectory and not the counterfactual one. And here, typicality arguments, etc., come into play. Typicality arguments are about the typicality measure of counterfactual states of affairs. And those are not observed, this measure cannot be deduced from the actual micro trajectory, because this is the only one that is real. What people do in those typicality arguments is either they take measures that are very useful in other contexts, for example, Liouville's theorem, ergodicity, and so on, and they take these measures and they use them in other contexts, for example, in distribution of probability over initial conditions. This is something else completely. These are irrelevant considerations. What people then do is that they take as a starting point the experience that the world is thermodynamics, and they choose a measure over the initial conditions of the universe in such a way that the actual will also be probable. But this is assuming the consequence, which is true along the actual trajectory, okay? So it's very good to use probability measures for predictions because we know what the experience is, but those don't explain this experience. And if we only want to repeat thermodynamics, we don't need to do anything. We know that thermodynamics is empirically suitable. So what we want to do is to explain it on the basis of fundamental physics. And fundamental physics doesn't provide the probability measure that some people think explains what's going on.
Okay, Isaac, are you all set?
Yeah, there's a lot of other people, so I won't.
Okay, I just want to remind everybody that we will have an additional hour from 3 o'clock to 4 o'clock for more questions. The person who's showing up next on my list is David Wallace. David?
Thank you. Thank you, Orly. I'm a little concerned that you're defining Landauer's principle in a way that's not conforming to the way I take the proponents of that principle to be defending from the literature. And I think in particular, you're defining it in a way that's using Boltzmannian conception of entropy in a way that more or less guarantees, for the reasons you give, that it can't hold as a fundamental principle because I can always cook up my partition in a way that falsifies it. But that Boltzmannian way of stating it doesn't seem what you find in contemporary defenses. I was looking at Charlie Bennett's paper on this from about 15 years ago, for instance, and he says, so the entropy decrease of the information-bearing degrees of freedom during a logically irreversible operation must be compensated by an equal or greater entropy increase in the non-information-bearing degrees of freedom and environment. This is Landauer's principle. Typically, the entropy increase takes the form of energy imported into the computer, converted to heat and dissipated into the environment, but it need not be, since entropy can be exported in other ways, for example, by randomizing configurational degrees of freedom in the environment. Now, it seems fairly clear that the notion of entropy he's using there has to be Gibbs von Neumann entropy, and indeed the rest of the paper supports that. And the case he's discussing, the randomizing configurational degrees of freedom, seems exactly to be the case, the kind of case you were considering in the counterexample. So shouldn't I really take the lesson here as being that one can't, or indeed can't take a Boltzmannian reading of the term entropy in Landauer's principle, but that the advocates of Landauer's principle are perfectly aware of that and have a different conception of entropy in mind?
Well, it's hard to tell sometimes which conception of entropy people have in mind in these discussions. So, describing this idea in terms of Boltzmannian framework is one way of seeing that Landauer's thesis is false. If you use other conceptual frameworks, sometimes the problems start much earlier, but they're not avoided in any case. So if you want to discuss, for example, Gibbs kind of entropy, it's much harder to see what's involved here because the change of entropy is the description of what goes on in entropy increase in that framework is extremely problematic unless you endorse some kind of partition to what in Boltzmannian cases we call macrostates, the coarse graining and so on. And so fundamentally, you repeat the same kind of idea. I think that Bennett's idea and his distinction between various kinds of the random information and the non-random information and so on, all fall under this same analysis. And the basic question is, how are we to understand what are the macro variables of the system and what imposes a preference for a certain partition of the macro variables over another? In fact, Maxwell's demon is exactly the thought experiments that brings this to mind. So maybe you would like to clarify a little bit what kind of macro variables or macro states you have in mind, or maybe those don't play no role in this construction of Landauer's thesis.
Well, again, as I read Bennett and other contemporary defenders, they're not appealing to a macrostate partition at all. They're making a division of degrees of freedom into information-bearing degrees of freedom and non-information-bearing degrees of freedom, and they're saying, relative to an arbitrary such choice, erasure with respect to information-bearing degrees of freedom is compensated for by increase in Gibbs entry relative to non-information-bearing degrees of freedom.
No.
But I mean, I'm just doing this. I'm sympathetic to that view, but what I think isn't actually relevant here. My real point is just that they're very clearly not appealing to anything like the Boltzmannian conception. So I'm just sort of concerned, just as a matter of charitable interpretation, that defeating arguing how on a Boltzmannian conception of entropy, Landauer's principle must be false is in some danger of attacking a straw man.
I think that if you try to think in terms that don't involve macrostates, then you're actually unable to describe what a computation is in the first place. Because a computation is carried out on a system, for example, the laptop on which I'm looking now. This is just a system with some actual microstate and micro trajectory. And if it flows in space, with nobody looking at it and nobody measuring it, then all that there is this actual micro process. And no computation takes place at all because there is no ascription of the values 0 and 1. So unless you choose some macro variables of the system and call those 0 and 1, you don't have a computation at all. And once you do this, you partition the state space into macrostates, that is a set of microstates that stands for 0 and another state, a set of microstates that stands for 1. Those are macrostates, generally speaking. This is why I think you cannot even account for computation unless you have a partition to macrostates. And then all the formulations of Bennett and others fall into the same line of argument.
So that may or may not be right, but it seems a pretty radically different form of criticism from the one that you presented in the talk. That's really all I'm saying.
I don't see why it's different, but I will be very curious to hear more about this now or in another opportunity, because I don't see that it's different.
Okay, let's not push any further now.
Okay, thank you very much, David.
Thank you.
We have time for one more question now. And again, if people have additional questions, if you could save them until 3 o'clock. I want to make sure we have time for people to take a break before Katie's talk at 1 o'clock. The person I have next is Lev.
Maybe I'm a simple-minded physicist, but for me, second law of thermodynamics is that if I take an ice cube from my freezer and put it in a glass, then it will not become bigger and the water will not boil, but it just will go in another direction. As far as I understand, I can explain it to my students very well by fundamental physics. I can do it, never mind if it's mechanical, it's classical or quantum physics, plus some mathematical statement, which is, for me, is the second law of thermodynamics. Thermodynamics is not fundamental physics. Fundamental physics, and I think, yeah, you present it in the same way, it's an underlying exact theory. And given this exact theory, plus some mathematical statement, can allow us to derive that in most cases we will see the correct behavior of ice, the behavior of ice cube in the water as we see it. So for me, it's just the fact that given the macro description, most of micro description will go to increased entropy. In fact, in both directions, past and future, but there is no paradox. This paradox can be solved. So clearly, physics will not solve mathematical statement. And all what should be proved is just this mathematical theory. So what's wrong with this position?
Very, very generally, of course, you can, when you teach your students thermodynamics, what you teach them are the empirical generalizations from experience along the actual micro trajectory of the world. And assuming that the future will resemble the past, this is a very useful way of thinking about the world. The question that I'm interested in is about explaining this fact. That is, why is it the case that the world is like that? Can we explain why it is, over and above just describing the actual trajectory? And here you said yourself that there are two problems. First of all, the symmetry problem, which you said can be solved, and it can be solved if we introduce assumptions that are not taken from fundamental physics. This is one. Second, you mentioned that you appeal to the notion of most. Most of the microstates are like that, but I don't know what the term most means. Most assumes a measure, and I don't know how to derive this measure from fundamental physics in the standard way of thinking about this. When people apply a probability measure over initial conditions and think that it applies to counterfactual worlds, and they choose the measure in such a way that it will yield that the actual is probable, this does not explain why the actual is like that. It's just very useful as an empirical generalization.
And I don't think that there is any, it's not big problem, the time symmetry, because it's a question, the system is open or not open, how I prepare it. I have to make a closed system, then the entropy will go up. And I cannot do this. And so there is a very small number of states which will give to this special behavior. I don't have tools. I didn't to prepare my ice cube in this way. So since most of the states will lead to this normal behavior, I'm not surprised to see this normal behavior. And of course it should be most, because we know there are some fluctuation. In principle, sometimes it doesn't go like this. So look, I don't see the problem.
It's actually quite simple. I don't think that we disagree about the fundamental points, but about the emphasis. So for example, if you consider an open system and you bring into consideration all the degrees of freedom, so that you have a bigger system that in the end is closed, just so that you can have a complete state space. In that case, the anti-thermodynamic behavior of your subsystem is compatible with physics. It's possible. Why don't we see it? Well, that's the question. You say that we don't see it because this is very rare or unlikely and or atypical and so forth. And the question is, how can we prove that it's atypical? I know that it is atypical. In my freezer also, you know, the ice behaves in the same way that in your freezer. However, my question is, how can I prove this from fundamental physics? And the point is that I think, is impossible. You bring in notions of most. You bring in the symmetry breaking assumption. It does not follow from fundamental physics, even given appropriate dynamics and some initial conditions.
Great.
Okay.
So I'm sorry I have to interrupt, but I'm sorry about that, Lev, but I want to make sure people have a chance to take a quick break. We'll reconvene at 1 o'clock for Katie's talk. So, yeah.
Thank you very much.
And thank you so much, Orly. That was a wonderful talk.